Hi, good morning, everyone. So, as I promised in my last video, that I will take you through ANOVA, which is called Analysis of Variance, in this video, and I will also share some good examples of analysis of variance. And in a very simple way, I will tell you what is ANOVA and when to use ANOVA and how to use ANOVA, right? So, let's start with this. ANOVA. Actually, it is a hypothesis testing, okay, where we are comparing the sum of squares or in direct way variability between and within. So when we say variability between, it's also called signals, and variability within, which is also named as noise. I will also let you know when I will share the MINITAB part of that. Okay, so if you are comparing or if we are comparing variability, so that's why it's called variance or indirect way analysis of variance. So this is a common question people will ask. In reality, we are comparing or we are checking the difference between, let's say, shift A, shift B, shift C, or vendor A, vendor B, vendor C, but the checking or the testing is done through these signals and noise. So that's why it's called analysis of variance. Okay, let's move on. Now, when to use ANOVA? Mostly people are not very clear on this part. So let me tell you, when you have always you have the axis, which is your inputs, and then you have the output, which is your y. Okay, so if you have a categorical inputs and the continuous y, then only we have to use ANOVA. Now, what is the meaning of categorical inputs? So categorical input may be the ordinal or the nominal. You remember in our last video, I shared the example of shift 1, shift 2, shift 3 throughput rate of some particular machine. So shift A, shift B, or shift C, or if I say first shift, second shift, third shift. So these are nothing but the categorical factors. So these are called X. And for each shift, you are getting the throughput or kgs per man hour, or kgs per hour, or liters per hour, or the flow rate of the particular machine, and you will get the rate. So those are your continuous y. So if you have more than two categorical factors, so here we have shift 1, shift 2, and shift 3. So that's why we are using ANOVA. Now maybe you will have a question, if you have two categorical factors. If you have two, then you have to use two test or two sample t-test hypothesis testing. If you have only one categorical factor and you are comparing that with some particular reference value, then you have to use one sample t-test. And I'm assuring you, in my coming videos, I will also share two sample t-tests, one sample t-test, and all these things. Okay, so for ANOVA, if you have more than two categorical factors and you have a continuous y value, then only you have to use ANOVA. And in between, I was also thinking, if maybe in my upcoming video, sorry, I will also share with you the different forms of data, like categorical, continuous, what is the meaning of discrete, what is the meaning of attribute data, and all these. Okay, so for ANOVA, it is very clear. If you have more than two categorical factor and you have continuous y values, we have to use ANOVA. Let's move on. How to use ANOVA? Now we are very clear on two things. If we have more than two factors, two categorical factors, more than two categorical x values and a continuous y values, we have to use ANOVA. The second thing is, if we are checking or if we are comparing shift A, shift B, shift C, vendor A, vendor B, vendor C, or more than two x's, then we have to use ANOVA. But there are some steps before checking or before doing the ANOVA. So first step is always you have to check the group variance, which is nothing but the variance testing, whether the variance of vendor A, vendor B, vendor C or shift A, shift B, shift C, or maybe I'm checking maybe the age of uh, age, or maybe let's say the salaries of of group A, group B, group C. So first of all, we have to check whether the variance are equal or not. That's the first step. And then if the variance are equal, we have to go with the checking or identifying the mean difference, which is actually the ANOVA. Okay, maybe the question will come in your mind, if the variance are not equal, then there are different testing that's called Walsh test. Maybe I will in my coming videos I will also touch upon that part. Okay, so for now I will also show you in Minitab how you can do these kind of testing. If you still remember, in the last call or in my last video, I have shared the data of line A, which has shift and these kind of data points, so which has three shifts: shift 1, shift 2, and shift 3, correct? And today I'm also coming with another line data, which is line B data. So we have another three shifts: shift 1, shift 2, and shift 3, right? There is some difference in these data points, obviously, and we want to check through Minitab what Minitab will say about these data points. Okay, let me just copy this data point and paste it in the Minitab for you. So if I just paste this data point into Minitab and let me remove all the old information in this. So what you have to do, you remember in my previous video I shown you go to the stat, go to the ANOVA, one way ANOVA, but please don't forget the first step is test of equal variance. So you have to click on this test of equal variance and your response will be data A, right? And your shift is shift. In the graphs for now I'm not actually checking anything, so I'm just want to check whether the variance are equal or not, so that's why I'm not doing anything. This is the confidence interval, which is 95%, so we are saying that we are okay, or we are 95% confident on the results whatever we are getting from our analysis. Okay, and then if I click OK, you will see the session window, your results has been pop up. Let's see what it says. Okay, so it talks about the equal variance test for the three shift. You can say shift A, shift B, shift C, or shift 1, shift 2, shift 3, and you have, these are called number of data points. So for shift 1 we have 12 data points, for shift 2 also, and for shift 3. As we are checking the variance, so obviously we are comparing their standard deviation, and this is their confidence interval. I will also maybe in my upcoming videos I will also touch on this part, what is confidence interval and how to get these kind of confidence interval. Okay, but for this video let's focus on ANOVA. Now if you see on the bottom, you are getting a p-value of 0.488, which is called multiple comparison test, and the most famous test is called Levin's test, and for this the p-value is 0.473. Believe me, in my upcoming video I will also going to share what is the meaning of p-value, but p-value is a very important value, which is also called the probability value, or probability of in which our test can be failed. Okay, but in more detail I will share in my upcoming videos. So for now, if your p-value is less than 0.05, then we can reject the null hypothesis, but in this case our p-value is very high than 0.05. What is 0.05? Which is our significance level. This is called alpha risk. Why it is 0.05? Because we set our confidence level of 95%. So remaining is called alpha risk, or the significance level in which our test or our data or our hypothesis can go wrong, correct? So in our case we are getting a p-value of greater than 0.05, which means we are accepting the null hypothesis, we can't reject it, and we are saying all variants are equal. Now as we have done the variance test, so the next step, or step number 2, is to do the ANOVA. Okay, as I mentioned, if your variants are not equal, then there is a separate test which called Walsh test. okay, that we have to do. Now let's go and check in ANOVA. So this is called one-way ANOVA and analysis of mean. So let's go to one-way ANOVA. You have this response is data A, and please don't forget these two options. I'm always selecting the first options because our data is in one column. Okay, and then in the shift factors, you have to select the shift, right? In the graphs here, mostly I select 4 in 1. I will also share maybe in my next video what is these graphs all about. Okay, and then mostly I'm not selecting this, but in my next video I will also tell you assuming equal variance, what's the meaning of this. Okay, and then yes, 95% assume equal variance. Even you are not assuming in this case because our variance are equal, we have already checked, so mostly we have to tick on this. We are assuming the equal variance. Okay, and then in the result part, yes, it's mostly on the model summary, analysis of variance, and all these things will pop up in the session window. Okay, when you click OK, as I mentioned, I will share in my next video what is the meaning of all these things. Okay, in my next videos. Now, and these graphs as well. Let's go to the session window to understand what our ANOVA test says about these data. So again, our null hypothesis means are equal, alternative hypothesis means are not equal, and these are the alpha values. Now let's go and see. Okay, so first thing is DF, which is called degrees of freedom. Okay, mostly we take n minus 1. Now if you have 3 shift, so 3 minus 1, which is 2, this is called degrees of freedom 2. Why n minus 1? Maybe we'll talk in different videos, because there is a very detailed video which I'm creating for degrees of freedom. Okay, now the errors, which is 31, so which talks about the total number of data points for each shift. Now let me brief you how we can calculate this 31. Now if you see, we have data point for shift A. How many? Total 12 data points. So 12 minus 1, which is 11. So 11 degrees of freedom for shift A, right? Or shift 1. Now we have total 12 data points for shift number 2. So 12 minus 1, again 11 for shift number 2. So 11 for shift number 1, 11 for shift number 2. So total is 22. And then you go to shift number 3, and if you see how many total data points, we have 10 in shift number 3. So 10 minus 1 is 9. So 11 plus 11, 22 plus 9 is 31. So this is you can see here 31. 31 is the degrees of freedom for errors. Errors in the sense within variation, as I told you in the first video. Okay, so 31 plus 2 altogether is 33. You can see the total degrees of freedom is 33. This is one way, or the other way is total 34 data points we have, minus 1 is 33. So degrees of freedom is very simple, and minus 1 you can calculate in that way. Adjacent sum of square, which I already told you in my previous video. Then we come back to the mean square. Mean square, what is the meaning of this, or what is the formula? It's very simple. So sum of square divided by degrees of freedom. So 18.833 divided by 2, you will get your mean square value. Okay, let me just increase the size of this. And same way, you have 163.86 sum of square divided by 31, you will get your adjacent mean square. Okay, and the F value is nothing but your shift or signals mean square divided by errors mean square, you remember, or noise. So you remember when I shared the information about ANOVA. ANOVA is talk about two things. One is between, which is called signals, and the other one is called noise. Okay, our target, our actually assumptions to have the good analysis of variance when we have more signals value instead of noise value. If you have more noise value, obviously you have less F values and more P values, indirect way I'm telling you. But now here F value, how you can calculate, you can calculate 9.451 divided by 5.286. You will get a F value. Now, what is the meaning of F value? So this is a table, as we have T table, Z table in the Z test. Here we use F values, and from F table we can get the P value. Okay, when I will share the information about P value later on, I will tell you how you can calculate the P value from different table, which is Z table, T table, or F table. Okay, but for most of the interviews, you may be asked as what kind of test we use for ANOVA. So please remember, we have F values, which, or F test, which we are using for ANOVA, and how you get these values is nothing but the mean square values of signals divided by the mean square values of your noise or errors. Okay, so by looking at all these data, your p value is 0.185, which is greater than 0.05. So you can say simply by looking at the p value that all the three shift information of the throughput are equal, or all the means are equal. It means you cannot reject the null hypothesis. So in this case, all the means are equal. Okay, so this is what we can conclude from our hypothesis testing. Now I want to share one more data. This is from shift number, line number B. So when you copy this, and let's say, let me paste it here. Okay, so you have same shift 1 2 3 4, 1 2 3, and these are the continuous data. Again, you have three shift, it means three categorical factors, and you have continuous Y. So you can understand we have to use ANOVA. ANOVA is having two steps, so always go to start, go to ANOVA. First is test of equal variance. Here you have to change the data. The response is data B, which you can see here, data B, and then the shift is shift 1 in this case, which is column number C7. Okay, I'm not selecting any graph because I'm just checking the variance are equal or not. When you click OK, in the session window you have your results. Okay, so this is the results of data B, and if you see here, this is again the total number of data points, standard deviation, because we are checking the variances, and here is your Levens test p values, which says 0.660, which is higher than 0.05. So we can't reject the null hypothesis. So we can say on the basis of this, all variants are equal. So when we do ANOVA, we have to select assume all variants are equal. Okay, let me just show you very fast. Go to ANOVA and then select one way ANOVA. Go to response, select this, and here if you want, now you can also select the box plot to see whether there is a difference or not. Okay, and then click OK. In comparison, okay, I will take this in my next video. What's the meaning of this? In the option, always take this assume equal variance, because you already checked whether the variants are equal or not, and click OK. So when you click OK, I will talk about these things later on. Okay, let's go to the session window and see what's the meaning of this. So now if you see in this ANOVA table, again you have the three shift, you have degrees of freedom, you have your adjusted sum of square, mean square, F values, and P values. But in this case, you can see your P values is 0.000, which is very, very less than 0.05. So in this case, we have to reject the null hypothesis. It means at least one mean is different. Now, if you want to see which mean is different, so the best way is to open the box plot, which I have selected this time. So here you can see simply by the box plot, shift number 3 is having very high throughput rate. It means something is happening with respect to line number B in the shift number 3. Why we have very good results, or why we have very good or very high throughput in shift number B? So we have to go and do the deep dive analysis. What is happening? What kind of things are happening in the shift number B for the throughput? Why it is coming very high? So that's how you can use ANOVA hypothesis testing to check which shift is generating more throughput or which particular line is generating more throughput in which shift, and you can do the deep dive analysis. So that is why it is very, very useful for us. So I hope you enjoy this video, and as I said, I'm definitely going to share some more videos about p-values, about the different charts that is coming in ANOVA, and also the different tests that we are using or we are doing in the hypothesis testing. Thank you very much.